Hello viewers and welcome to another episode of Space Science with Python. Today we will set up a small Comet database using data from the Minor Planet Center. And this database that will be created using SQLite is then the fundament for our future videos where we will create some space scientific data insights into the comet population in the solar system. So we will get an understanding of the comets, where they come from, the distribution of the sizes, their dynamical properties, and so on. And the video today is like the fundament of all these videos. As always, I created a new branch and a new folder, which is today called Comet Database. So all the code of today's session will can be found in this folder. And the data, you don't need to download it. We will use Python to download it from the Minor Planet Center. But before we dive into the data, maybe just a small note about some current comet. It's namely C2021A1, Comet Leonard, which is currently visible in the morning sky, as they also stated here in the tweet. So the comet has a tweet account. It's now only 5 mornings left to observe Comet Leonard from the northern hemisphere. So be quick, as they say. Grab some binoculars or a telescope and take a look at the comet. It's a quite nice view. It's not as bright, of course, and huge as the Comet Hale-Bopp or the Halley Comet, but if you want to see a comet with your own eyes, just grab some binoculars and go outside and watch the skies. There are also some maps here on this Twitter account. The link is in the description that will help you to find the comet. So the comet database we will create today consists of all data or all comet data that are known to humankind, so around 500 or 600. And as some of you may know, the comets are small dirty ice balls that conserve the state or the state of matter, the composition of the early solar system, and can be described as dirty ice balls, with minerals, organic matter, dust, and so on. We will take a look at the shapes of comets, their origin, in a future video. Today it's basically about fetching all the data and doing some data engineering to compute some orbital elements and some properties, and to feed the database that is then being used in the upcoming video. Now the data we want is on the Minor Planet Center. If you click here on data, the link is also in the description. You find here a lot of different zipped files with the current databases for near-Earth asteroids, near-Earth objects, or here the orbit elements for the currently known comets. Last time we were talking also about the SBDB query API, where we can query the NASA REST API service to obtain all the data. But today we will simply use the Minor Planet Center file. And let me here quickly copy the address. Again, I already created or set up my environment here in the remote Docker container in VS Code. Here already some imports, and you see here also some kind of Python script I imported, data fetch. It's in the auxiliary folder, so beside the normal video folders 3, 4, 5, and so on, I created a new one which is simply called auxiliary, and there I will just add some functions or classes that will be used in the future, so to prevent redundancies. So for example, some scripts to create a database or so will be then being stored there, so we just can simply call the corresponding functions. Now, first of all, the data fetch function, let's have a look at this. It's quite simple. The Python file consists currently of only one function, namely to download a file. It uses a file name and a path where it should be stored locally. it creates a directory and then uses the URL lib request or URL retrieve functionality to download the file and store it in the requested folder on my machine. So it will be also stored here in the repository. And I think the size of the files is not very big. So for example, the Comet database will be also uploaded on GitHub. So you can either recreate it or just simply use what's on GitHub already. So the very first command should be to download the files. So first we will create the path where we want to store it. So dl path, we simply call it raw data. And the URL where the file is, we just stored it. It's the Minor Planet Center extended files, Comet els JSON gzip. And now we can simply say data fetch dot download file dl path and then dl URL, so we can download this file. Let me first execute this script here. Yeah, so we have to run all. Yeah, and now it works. You see a new folder has been created, raw data, with the gzip file. Good. We need also for our computations later spice and some kernels. So the kernel meta file is already in the repository. Just take a look at this. We just need them later, some kernels to compute some properties. And now we can read in the Comet data. So let's call it C_df for data. So Comet data frame, where we use pandas read JSON. And the name is, it's stored in raw data / Comet els.json.gz. And since it's compressed, we need also to pass the argument compression. And this one here is gzip. So let's execute it. No error was spawned. So let's check. And we have some data here. So we have something called orbit type, designation number, perihelion distance, eccentricity, perihelion, argument of ascending node in degrees, inclination, and so on. So we have a lot of different parameters. And well, do we have all parameters? Well, of course, if we want to compute state vectors, we need the orbital elements, of course, but we need also the epoch, right? So we don't see here now any epoch, so no angle or something like the argument of perihelion. So this is actually missing. We only see the distance, the perihelion distance, and the epoch year and month. They correspond only to the orbital elements. So what is now the argument of perihelion and the mean anomaly? Well, for this, we have the year of perihelion, the month of perihelion, day of perihelion. And so at this year, at this month, this day, the comet was at the perihelion. So the mean anomaly at this point was 0. So based on these three values, we need to compute, of course, the argument of perihelion to get the data. Yeah, the argument of perihelion is of course stored here. It's of course the alignment, the pointing of the argument of perihelion, but we don't know the exact position of the comet, and this is where these three values come into play. So first, we need to create the epoch for this, and for this one we will say, okay, let's create the UTC date first. So epoch UTC date, where we can say, okay, CDF apply lambda, and we use the string of the year of perihelion. So year of perihelion plus, and we create it in a way that's later can be understood by spice. and plus string plus the string month of perihelion. Ah, come on. Month of perihelion plus the minus plus string day of perihelion, but that's not 100% true because, wait a second, there it is. We have here the day is given in decimal numbers. So you see here that's now 29 days at 29.7 and so on. So we need to take the day, and this decimal number needs to be converted into a UTC time string. And we'll do this in a moment. Of course, Spice can also understand decimal numbers and so on, but this may be helpful to have some more human readable format. And this is being applied along the y-axis. So let's have a look and let's see how it looks like. The Epoch UTC date. Okay, this looks good. And now we need to to create something like a we need to know the time of this decimal number. There are a lot of ways. I mean, we can simply do it quick and dirty. We just define some placeholder date time object. Date time. Yeah, I can say year is 2000. Month equals 1 and day equals 1. So it's basically midnight time, date time. So again, this is really quick and dirty. And then we can say, come on, CDF log epoch UTC time. Now computing the time. Take the day of perihelion this time. So we can apply lambda function again. And what we do, we just simply take our pre-time, simply just a placeholder, say date time dot time delta, days equals to z, and the z is the x is then the entire day, and then from here we just take the resulting times. So we can say that we take this one here and only want strf time. strf time, yeah, we only take hours, minutes, and seconds. So maybe we should make a line break or so to format it a little bit nicer. Let's have a look. Date time is not defined. Okay, and that's not a problem. There it is. There's another error. Time delta is not defined. Yeah, because I have to make a brackets here and remove this one. And now we can take a look at the UTC time. And now we have the corresponding times. So now we need to merge the Epoch UTC time with the UTC date. So basically what we need to do is we need to define now the Epoch UTC. Let's say just UTC is equal CDF apply lambda x, where we use simply the Epoch UTC date plus the corresponding UTC time. And of course, other time formats can also be used by SPICE, also decimal numbers and so on. But we are just starting with the tutorial series, and we are now very, let's say, familiar with the format of UTC date, then this T separator, and then the time. So we will stick with this one, and with this lambda function, everything is quite readable. So of course, in the future, we will do this a little bit differently, but here now let's stick with this format. And now we can also compute now the corresponding ephemeris time. So basically it's this one here, it's Epoch ET, and it says CDF of Epoch UTC, and then we apply the SPICE function UTC to ET, so lambda x SPICY dot UTC to UTC to ET of x, and that's basically it. Okay, cool. So we have now the ephemeris time, and the epoch now corresponds to a mean anomaly of 0 degrees now, because at this time the comet was at the closest distance to the sun, so at the perihelion. So at this time the mean anomaly should be 0 degrees. Now we can compute also other parameters for our database. We can also say, okay, we can compute it, but maybe we want to query also it simply from the database with SQL. We can say semi-major axis in AU. We would like to compute this one with CDF, and then we apply again some basic logic. Lambda x, for example, the perihelion distance, which was given in AU, divided by 1.1 minus the eccentricity. And this is, of course, if the eccentricity is smaller than 1. So if the eccentricity is larger than 1, we actually you can also compute the semi-major axis, but let's only compute the semi-major axis for orbits that are circular or elliptical shape. Good. This should be also formatted a little bit better. Semi-major axis. We can also compute something like also the aphelion, so the most distance, so the larger how to say it, the sun farthest point, so the opposite of the perihelion, aphelion AU, and it's basically like the same logic as here, almost. Here we say 1 plus the eccentricity times the semi-major axis, so x times semi-major axis. And also here the eccentricity has to be smaller than 1, otherwise it would be infinity. So aphelion in AU, so we can compute this one as well. And now we can create our database, and for this one we will also create a new folder. So you may ask why I'm doing this here in Python. Well, if you want to recreate everything, you don't have to make a right click and then create folder and so on. So everything is here in the Python code. We create a database for the comets. Later we will maybe also add asteroids or for spectra or whatsoever other databases. So we will gather all information, all databases here in this folder database. So yeah, let's create one. If it exists, it's true. And now we can create our database. So we use SQLite 3, which is like MySQL or like any SQL database, but it is completely embedded. So the entire database is in one single file. You can move this even to your Android phone, I think, or iPhone. So the small embedded devices like smartphones, they also use SQLite for the contact database and so on. So it even works offline. You don't need to set up any server on your device. You can just simply query it. And yeah, for small databases, it's quite sufficient. So there's no need to make some overkill with MySQL and so on. So now we create our database here. We connect it, and if it doesn't exist, it will be created. And then we set up a cursor. So if we execute this command, you will see that a new folder will pop up called database Comets, and then the MPC Comets DB will be created. Exist, okay. And there you see database Comets MPC Comets.db. We can move to our Finder and we see it's 0 kilobytes, so it's pretty empty. And now we can fill up the database. First of all, we need to define the table name and the content, and then we can add the data in there. So I just cached something. I already prepared it, so you don't have to watch me how to copy paste everything in there. So first of all, I execute create a table if it doesn't exist yet. So table is named Comets main, and there we will have primary key, the orbit type, perihelion and AU, semi-major axis, aphelion, eccentricity, and so on. You see here the mean anomaly. Mean anomaly in degrees is the default is 0. So the epoch that we just created corresponds to a mean anomaly of 0 degrees. So this is the default for every entry. So we can simply execute this one. Didn't commit it yet. And now you can create or fill up our database. So we use this command here. And this is simply a so-called execute many command. We insert or replace in our database the name, orbit type, and so on. We place it. The values are set up with placeholders, with question marks. And then we give the argument or the data frame as the argument in the correct order. So the designation and name, the orbit type, perihelion, and so on. This will fill up our database. And each entry here, line by line, will replace the corresponding question marks. Of course, Pandas has also some built-in functionalities to write directly to an SQL database. But here I just wanted to show you how to do it that way. And then we make the commit, and then we close the database. So let's, did I create it yet? Oh, I think I should maybe delete this first again. Delete permanently, yes. So let's re-execute this one. Then this one. This one. And now we can take a look. If you have, there's some viewers you can download, for example, the DB browser for SQLite. Now this is here set in German, but it's okay, I guess. And there you see now the content of the database. The name, the orbit type, the perihelion, semi-major axis, the aphelion, the eccentricity, and so on. And for the eccentricity larger one, we didn't compute any semi-major axis or aphelion, so we just leave it empty. And here the mean anomaly. The magnitude slope parameters, yeah, don't get bothered by these values. We will get to this in the future. And yeah, here's the corresponding epoch in UTC and the ephemeris time. So we have now a small database. You create some SQL queries to obtain the data. For us, this is now the fundament for our future videos. So it may be a little bit boring for anyone who's familiar with very simple data engineering tasks, creating SQLite databases and so on. But maybe you learned something, how to set it up, how to download it, how to write stuff into the SQLite database. And next time and afterwards, we will have some really create some deep insights of the content. So we will take a look of the distribution of the comets. So what is a P? What is a C class? How do they differ? Are there any relations, astrodynamical relations to larger planets, for example, Jupiter? So small spoiler, yes, they are. But we will compute them by ourselves. So we will see how to do it. We will also create some nice visualizations using Matplotlib. And then you will get a better understanding with Python and with your programming skills. You get a better understanding of the comets and where they come from, how they behave, and maybe we will also see if we have some still unanswered questions or not. So yeah, again, the code is on GitHub. And as always, take care, have fun coding, and see you next time.